Hello everyone, how are you doing? Today in this video we're gonna discuss changing coordinates. Changing coordinates means if you have x and y coordinates, how this one can be changed to a polar coordinates. Remember in pre-calculus when you had an ordered pair here, x and a y, you could use polar coordinate, which instead of x-axis, instead of the origin you had the pole, and instead of x-axis you had polar axis, and from the polar axis you went counterclockwise on a specific angle, and from the pole it took you some distance to get to that point. Therefore, the Cartesian is represented by x and a y, but the polar represented by the theta and a r. And we do know that in here, your x squared plus y squared is r squared. And also we know that theta is the arc tangent of y over x. And you have to be very careful. Arc tangent is always maneuver between negative power to power 2. These points are excluded. Therefore, I take the absolute value and I always find the reference angle. Therefore, if the ordered pair in the first coordinate, the reference angle is the angle I'm looking for. If the ordered pair is in the second coordinate, you have, in order to find your angle, you have to subtract the reference, because I'm going to call this one theta prime. That's your reference. In the first coordinate, the theta and theta prime are the same. And in the second coordinate, I'm sorry, I shouldn't have said theta. Theta is equal to pi minus theta prime. In a third coordinate, your angle would become pi plus the reference. And in the fourth coordinate, which x is positive but y is negative, your theta is always going to be 2 pi minus the reference. Therefore, when you do arctangent, you have to find the reference and apply one of these methods to do it. And also we knew that the cosine of theta is equal to x over r. Therefore, x is always r cosine theta. And this is how you went from a polar to the Cartesian, and your y was r sine theta. Therefore, this one, you go from a polar to the Cartesian, and for this one, you go Cartesian to a polar. We remember this in pre-calculus. Then if you remember in calculus 2, sometime you had an equation represented by a polar form. And if you remember, this was your A, this was your B, and if A is equal to B, the graph is going to be a cardioid. Therefore, if this is my pole and this is my polar axis, when the theta is 0, this is 4, your R is 4, and if the theta become pi over 3, cosine of pi over 3 is 1/2. 2 times 1/2 is 1. 1 plus 2 is 3. Therefore, on a 60 degree, I need 3. And on a 90 degree, cosine of 90 degrees, 0, you get 2. And on a 180 degree, the cosine of 180 is -1. Therefore, that becomes 2 minus a 2 and is a 0. And my graph become a cardioid. Then the other piece is symmetric, and that was the graph of a cardioid. And in calculus 2, they ask you to find the area. Remember in calculus 2 what you did, you divided this one just like you cut in a pizza, in a smaller pieces, and you call this one sector. And the area of a sector is nothing the same as the area of a circle. For area, you always take half the angle they gave you. For a whole circle, the angle here is 2 pi. For area, you need half of it. You take half angle r squared. For this sector, if the angle is theta, you need half of it r squared. And since this is a cusp right here, and the function is not differentiable at that point, you have to break your problem to 0 to pi and double your answer. And you say 1/2, and remember in here, that's the part of your theta. And therefore we call it d theta, and that become 1/2 r squared d theta. And what was your r? Your r was 2 plus that one, and that become 2 times 1/2, 2 plus 2 cosine theta squared d theta. And you know you can square that one, and that become 2 plus 8, that 4 times 2 is 8 cosine theta plus 4 cosine square of theta. You know how to integrate that, which is 2 theta. You know how to integrate that is 8 sine theta. But for this one, you have to use half angle. And when you use half angle, that becomes 4 times 1/2 is 2. 2 theta, 4 times 1/2 is 2. And that becomes 2 sine 2 theta divided by 2. Therefore, you know how to integrate it and you can evaluate it. But do you see how much trouble you have to go through in calculus 2 to find the area of a cardioid? Let's use double integral. If you're gonna use a double integral, I have to divide this one into little squares and take one of these, which is delta x delta y, and I don't know which square I'm going to call it. I'm going to call it the delta x of the ith rectangle square, delta y the ith. Then here you have to go back and change this one to a what? Change this one to Cartesian. Because everything has to be function of x and y. Therefore, if I multiplied this one, if I want to change it to a Cartesian, your r is going to become x square root of x squared plus y squared equal to 2 plus cosine is nothing except x over r, and your r is this. Then if I get a common denominator, I get a square root of x squared plus y squared equal to 2 square root of x squared plus y squared plus an x over a square root of x squared plus y squared. And when I do common cross multiply, this become x squared plus y squared equal to 2 square root of x squared plus y squared plus an x. I want you to just look at it for a few minutes. And if you want to solve this one for x and a y, do you think it's easy? Because you have to solve for y. You have to bring everything has y in it to one side. You have to square to get rid of that one. And you know that problem is pretty much not going to say impossible, but it takes days and days. Lest if your region is a circular region, let's not divide it into the rectangle. Somebody said, then what can we do with it? Then I'm going to take that region and I'm going to assume this is a Valentine's pizza, and I'm going to cut my pizza like this. Therefore, I'm going to change my angle from 0 to pi, and I'm going to call each of them a d theta. And I'm going to divide this one, but also remember, that's too big of a piece to give it to somebody. And these are your r. Also, I'm going to divide it. My r becomes 0, my r becomes 1, my r becomes 2, my r becomes 3, and my r becomes 4. And I'll pick up one of these pieces of pizza. Therefore, that piece of pizza is right here. And this is not a square. I know here r is 2, here r is 3. I know this one is called change in r. But this is round. This is called the arc length. Arc length, like circumference, which is 2 pi r. If you remember a few minutes ago, I said area always consume half of the angle you give them. But circumference of a circle, you use all the angles. Therefore, if I want to find the arc length of that piece right here, you have to consume all the angle. Therefore, if this angle is theta, you have to say the arc length is theta times r. Therefore, here, this is r times theta. But let's talk about that theta. My theta was from 0 to pi. This is part of my angle. Therefore, that is a d theta. Then from today, you have to know, if this one was a rectangle, we call it dxi, dyi. I means the number of a rectangle. Could be the first, the second, or the third. This is the same as that piece. And that piece is r dr d theta. Then from today you have to know, if you are going to change the coordinate, and if you want to move from a Cartesian to a polar, Cartesian deal with x and a y, polar deal with r and a theta. Therefore, on a double angle, here you had dy dx. This x is fixed because I'm finding the area, but this has to be function of x as the lower, and this one has to be upper. But if you change it to a polar, this is your theta. My theta 1 go to theta 2. That theta 1, it had to be in radian, real numbers. That theta 1 must be less than theta 2, like pi over 6, and the upper is pi over 3. But this is your r. This is r1, this is r2. But please remember, because this is the inside function, your r has to be a function of theta. Therefore, that r2 has to be function of theta, r1 has to be function of theta. And instead of dy dx, you put r dr d theta. Then somebody said how this r was resurrected right here. Remember, we said a few minutes ago that x is equal to r cosine and y equal to r sine. Then what is the partial derivative of x respect to r? Respect to r is cosine theta. What is the partial derivative of x respect to theta? Partial derivative of x respect to a theta is negative sine theta r, negative r sine theta. What is the partial derivative of y respect to r? Respect to r sine theta. And what is the partial derivative of y respect to theta? Y respect to theta, derivative of sine is cosine, r cosine theta. This is a matrix. What is the determinant of that matrix? This is a determinant, r cosine squared theta minus, because when you go backward it's negative, but there is a negative here. Negative times negative make it a positive, and this is r sine squared theta. And r is a common factor. You see cosine squared theta plus sine squared theta, and that r was born from the partial derivative of x respect to r, partial derivative of x respect to theta, and same thing for the y. This is called a Jacobian factor. I hope we get time to it. We talk about Jacobian factor, but somebody said, I'm confused. What does that means? Please remember in calculus 1, whenever you had the integral of 4 minus 3x squared, and I'm going to put the x right here, dx, here you have to use the chain rules, u substitution. That was your inside function. My inside function is 4 minus 3x squared. And the differential of inside function is negative 6x dx. Then that is the differential of inside function. I do have the x, I do have a dx. Therefore, I'm going to write x dx and 4 minus 3x squared. But if I want to change u substitution, basically I'm changing what? I am changing the variables in here. I didn't change the coordinate here. I'm changing the variables. But when I change the variables, instead of du, I make negative 6x. Oh, I multiplied the inside by negative 6, divided the outside by a negative 6. That's the plus 1. And that's become a du. Did you see when I change to a variable, you must have a negative 6 in here? And how did you add another constant multiples? Then when you go from a polar Cartesian to a polar, you do need that r right here added to it. Therefore, from today, you have to know this is the area in a Cartesian, this is the area in a polar. Let's do this right here, which was my cardioid. The equation of my cardioid was 2 plus 2 cosine theta. I want to go from 0 to pi because at that point I have a cusp. Whatever my answer is, I'm going to double it. But the smallest radius is 0. And the biggest radius is my boundary right here. And that boundary was produced by this. And that's your r. Therefore, your r go from 0 plus 2 cosine theta r dr d theta. Let's do that problem. What is the integral of r dr? Is 0 to pi r squared over a 2 from 0 to 2 plus 2 cosine theta d theta. Then in order to solve these is 2 from 0 to pi. And remember I have a 1, 2 in here and a 2 here. And I'm going to put the 2 outside and they're going to undo each other. And you have 2 plus 2 cosine theta squared d theta. Do you remember a few minutes ago I talked about calculus 2 and I said we used the sector and many students didn't know what the formula for sector is? And do you see we double it? Do you see how the 2 and 2 cancel? Do you see how you got 2 plus r squared is this one? Look what we got for the double integrals. For the double integrals, don't you think that 2 and 2 is gone? And it's exactly the same thing. But why double integral was easier? Because you didn't have to know the area of a sector. Therefore, you can do this one as we did for that one. Therefore, today, if you do have a region, and your region is circular region, instead of dividing into a rectangle, divide it into a sector and take one piece from a sector and call that area r dr d theta. And if somebody say where that r came from, that's your arc length. Your arc length is s equal to r d theta, and this is the change in r. Therefore, length times width. And that's where it comes from. And this is how we can apply the polar coordinate to finding the double integral. Next video, I'm gonna do examples. Have a great day.